Okay. In line with my usual habits, I will speak about state channels. But this time I thought I would actually be able to get to show you something as well. Briefly about me, if anyone has missed it. This is my, this year is my 30th anniversary of Erlang programming. I've passed through a couple of other areas like disaster response, telecoms, automotive, and I've been on the Æternity core team since 2017. And Dimitar and I mainly developed the state channels subsystem. I will call myself the lead developer since I'm the older one. So, of course, we'd have to think about what we actually need state channels for, or what are the use cases that are interesting to develop for. And, well, paying for coffee always pops up, as if people needed another way to pay for coffee. But the interesting thing is sort of the characteristics of various types of payment. And for example, you want to look at throughput, you want to look at response time, and you want to look at costs. And we're thinking that state channels may have a good fit for micropayments on the network. Briefly about state channels. As all other things on Æternity. If there are only Æternity people here, I can keep this brief. But channel objects are first-class objects on Æternity blockchains. That simplifies a lot of things, which I think has led to our state channels actually working, as opposed to many other projects that have difficulty getting out of the research stage. It also means that they're a lot cheaper than layer 2 solutions. The features we have some that require co-signing and basically progress the state in the state channel. Those are contract calls and payments, and they need to be co-signed. So the channels are one-to-one. In order, when you make a contract call or you make a transfer of tokens between the peers, both of them have to sign. We also have generic messages, and they are just blobs that you pass between each other. They don't require any signing. So that makes them extremely flexible and extremely fast. So the on-chain transactions are, first you create a channel object, a create channel transaction. When the channel is open, you can deposit coin into your channel. You can withdraw coin. You can post a snapshot on chain. And another thing you can do is you can force a contract call. If you believe that, for example, you're playing and it's your turn, and you have this great move, and your opponent doesn't want to approve it because it's too good a move. You can actually go to the chain, and if it's a valid contract call, you can force it via the chain. And then you have a couple of closing scenarios. The mutual close is where both people agree, and it's co-signed, and there is no dispute about the state. And then you have the unilateral close, which is solo close, which can be met by a slash, where you bitch about what the actual state is, and ultimately you settle. So at a minimum, you have 2 transactions, on-chain transactions for a state channel. And then you may have some on-chain transactions during the life of a state channel. And a state channel can potentially live forever, almost. You can actually disconnect, and the state is cached, encrypted, and you can resume it later. So this is kind of nice, because if you have spotty network or whatever, or your mobile goes to sleep, and the WebSocket connection terminates, you can pick it up again. So logically, the state channel is ongoing and could be ongoing for a long, long time. But the fact that you have at least 2 on-chain transactions make them a poor substitute, for example, for a spend transaction. It would be much more expensive to pay for something using a temporary state channel the way they work right now. So the way it's set up is, if Alice and Bob want to open a state channel, they actually have proxies on the node. And these can be on different nodes. And the protocol, for example, if Alice wants to pay Bob, is she sends a request to her proxy, and it sends a transaction back for her to sign. And then that signed transaction is passed on to Bob, asking him to sign, and that goes back to Alice. And now we have a co-signed state, and both have agreed to the updated balances. So, performance, once you're off-chain and you have tokens loaded into the state channel, these are from our test suites, so that would exclude network delays and also signing delays, because signing takes place automatically. It's all on the same machine, and in some scenarios, actually, the signing cost, where the same node has to perform or do all signing, that could be a CPU bottleneck, actually. But essentially, about 100 payment transactions per second on one channel. And if, for example, the node is serving 10 concurrent channels, you can get up to like 400 TPS in total. Contract calls are slower, but about 25 contract calls per second per channel. And the generic messages, or in-band messages, are quite fast, so then it's in the thousands. Now this is for one node. So, and if you have multiple nodes in the network running state channels, it scales linearly. So you could possibly also run, this is something I would like to explore a little bit. Yeah, you can have a node running the Æternity system and the chain, and then have some proxy Erlang nodes that are connected as a cluster, and they could all run as state channel proxies if you want to do a server and these numbers aren't good enough on your node. So, again, when you open a state channel, you create an object on chain. Now, normally you would wait for a number of transactions. You can specify this as an option when you open the channel, minimum depth confirmation. But then you'd have to wait for key blocks before you can start using the channel. You can set the minimum depth to 0, and then the state channel is ready to use as soon as you get a microblock confirmation on the create TX. We added the possibility to defer this. So as soon as you get the confirmation that your TX has touched the chain, you can send a message to your proxy saying that, okay, that's fine, let's move on. You will eventually get the minimum depth confirmation for whatever depth you've set. But again, we're talking at least 2 on-chain transactions. And So the idea that I wanted to show here then is to set up one channel to a market hub and just keep that going. This would be like your generic payment card. So we introduce Ingrid, the intermediary. And so Alice and Bob both have state channels to Ingrid. Now, at Universe 1, I talked about virtual state channels, which would be, well, we've sketched a description of how that would work, but we're not there yet. So this would be a different setup where we're using hash locks. And then a payment from Alice to Bob via Ingrid would look like this. Alice sends a generic message, actually, to Bob via Ingrid. Oops, don't want to touch that. And this is another thing we added recently, message forwarding. So if Ingrid has message forwarding turned on, she gets a generic message, and it's not to her. She can try to find a channel that she's involved in that has that pub key as a peer, and then she can pass that message on. So, so we send a payment request to Bob, and we provide a unique ID, and Bob takes that and generates a hash lock, which is basically a public and a private pair. So he passes on the hash lock back to Alice. Alice then calls a contract on the channel. Now, Alice or Ingrid would have installed the same contract on every channel here. So she does a contract call, which is, she says, new send to Bob, this is the amount, this is what Ingrid gets to keep, the fee. And we provide a timeout in terms of key blocks on chain. So within this time window, Bob would have to actually collect the money, and then the hash lock. So then this payment is locked inside the contract. Alice, or Ingrid, Ingrid forwards the contract call, essentially makes a corresponding contract call on Bob's channel. This is called a new receive. And Bob can collect by providing the secret. And this allows the contract to spend the amount to Bob. And of course, since Ingrid has to co-sign the contract, or the contract call, she now knows the secret. So then she can collect on the other side. Because obviously, Alice locked the amount plus the fee in the contract here. Now Ingrid had to put in the amount here, lock that into the contract. So that goes away here, and then she can collect the amount plus fee on this side. Eventually, Ingrid will have to rebalance the amounts on the channels, and this she can do with deposits. And of course, Alice and Bob would have to agree, which they probably want to, because if Ingrid doesn't have any collateral on the channel, then they're not going to be able to trade. Was this clear? So, the contract exists in this repo. It's called AE plugin _SCM. It's also actually in the Æternity repos. It's a test contract that we have for our test suite. And we have the entry points here, collect, receive. You can't read this anyway. But the nice thing about this is that practically all the checking, integrity checking, is in the contract. So there is not that much room for example, Ingrid to cheat. Also because of the timeouts, so Alice can actually get a refund. She gets her money back if the time runs out, things like that. So I have a demo. It's the most beautiful demo ever. As you can tell, I've spent the least amount of time possible on the UI. And I had this picture here in case I wouldn't have time to run the demo. But I do have time, so I will run it. Now, I decided to make this a useful exercise for me to use a Node plugin. So the server side is implemented as a plugin. And actually, everything runs inside the plugin right now. I implemented a registry. So I have customers and merchants, and the difference is mainly that the merchants can provide names and tags. So the names are unique, the tags are not. And I'm using gproc, which is a registry that the node is already using. I also, because I thought it would be useful, decided to encrypt the chat. So the actors on the market are able to chat with each other, and the endpoint encrypts using the other side's pub key. Unfortunately, the enacl function I'm using wants a particular nonce that is shared by everyone. So I think there needs to be key exchange and everything for this to be really useful. But a lot of things have to happen for this to be useful. For one thing, we shouldn't use hard-coded priv keys, things like that. I also had a group chat because what the heck. So you can, I actually only have one hard-coded group, and all the actors are joined to that group, but I thought I would add later some functions so that you can join and leave groups and do encrypted group chat. And then the hash lock payments. So I can show you this. I have a node here. I'm just going to scratch the database to begin with, and then start the node. Let's see, have you been playing with plugins? So essentially I just linked in the I have the dev mode plugin and the state channel market plugin in the plugins directory. And then I use an Æternity config that I've created in the demo directory, which specifies these plugins. So let's just run this. Now, it occurred to me when I was running this that it doesn't really illustrate the difference in speed between the chain and the state channels, because using dev mode, everything on the chain is instantaneous. But, so I have this, I click this seed accounts here, which just mines a few blocks and then distributes some value to some accounts. So I have some accounts to play with. I have 3 accounts that are viable, basically. The one account is used by the hub. And now let's, for example, connect my coffee shop. And the tags, I don't really use them, but if you go into the shell, you can query and list vendors by tag. But again, the user interface. Now, I'm also going to connect a customer. Now I have 2 to go. I can actually connect 2 here. So now I have 1 merchant and 2 customers. As you can tell, the customers are anonymous. The merchant actually has a name. It could have many names, and tags. We also have the on-chain balance. It's not going to change. And then we have the balance. This is the coffee shop balance here, and this is the market side balance. And here I have total market balance. So this is the sum of all 3 state channel balances that the market is running. So now I could, these are my 2 customers running, so I could pick one of those, and then I could, this is actually the pub key for Ulf's Coffee. I can pick the alias or the, well, that's just a UI thing. Let's pay an amount here. The UI should be dynamic if I had any expertise in UI programming, but I did instrument the logging so that when I send a payment, immediately that came from the coffee shop where it received the funds. And the on-chain balances didn't change, but the channel balances did, and the total balance as well, since let's make another one, and we can look at, for example, the total market balance there. It increases with the fee. And then you can also see that the market balances are shifting. It's actually shrinking here, and it's increasing here. Now I can also send a chat message. Let's say that I send a message to Ulf's Coffee, and you saw that message coming up there. I can send a group. This is not an extremely exciting demo, but it now the group message I should see. I see 2 log messages there, where the message was sent to all the members in the group, except the one who sent it. But again, so this is essentially how it works right now. The whole state channel market plugin is about 1,800 lines of code. So not very much at all. And well, obviously, a lot of stuff will need to be added. For example, all the exception cases, it's just doing happy case right now, assuming that the payments go through. Otherwise, it's essentially going to crash. We don't deal with the timeouts. We don't deal with refunds or anything. But this is just first proof of concept. And so it actually works reasonably well. And Metin and I plan to evolve this a little bit and maybe perhaps also field it on the testnet. And then we can see if we can actually also use the SDK and actual mobile clients. So do you have any questions?